So what can we do to identify these breakpoints? Well, the main statistical tool at our disposal is the control chart. So you assume that the quantity of interest is defined in terms of some random variable, and for now we'll assume that it's a random variable which is normally distributed. So population mean and a population variance. You can build control charts for random variables that are not normally distributed as well, but we're going to be working with the sample mean and the sample standard deviation, and so the central limit theorem will kick in at some point, and so we might as well expect, and so we might as well assume that our variable is already normally distributed. As an example, you could be looking at the inside diameter of some piston ring. Perhaps by design it's meant to be 74 millimeters, but there's going to be some standard deviation due to some common causes or potential special causes. But at any rate, the standard deviation is 0.01 millimeter. The measurement for us, the random variable x, would be the actual measured ring diameter for a specific specimen. So at given points, t1 all the way up to t uppercase n, these often represent time, but they don't always do so. You sample lowercase n observations. So for every location or for every time stamp of interest, you will make n samples. Xi bar is going to be the sample mean from the n observations at the time index I, which is one of the t1, t2, t3, all the way up to t uppercase n. And Si will be the sample standard deviation of that sample at a specific time index I. So I here is one of the tj's. So you will have a grand total of n such sample means and n sample standard deviations. That's a random variable as well, right? Now you can compute their means if you want to. So you have the grand mean, which is typically denoted by x bar bar. It is the average of the sample means at each of the capital N time indices or locations. It's an average of averages. And you have S bar, which is, careful here, the average of the sample standard deviations. A control chart is going to be a collection of observed values of a statistic. So at various time indices or various locations, you will measure the sample mean and the sample standard deviation of the measurements that you take at each of these times or locations. And you'll plot those as a time series. So you can imagine something that would look like this. This is the passage of time. These are the times when I've decided to sample my process, and I will compute the mean of my measurements. I might end up with something that looks like this. Now in practice, if instead of plotting the sample mean, you were actually going to be plotting the true measurements, you might get something that looks like that you wouldn't be plotting the sample mean anymore. You'd be plotting the observations. All of these measurements, X, are supposed to come from the same process, same population, in this case a normal population with true mean mu and true standard deviation sigma. And if you do know them, then you can use the central limit theorem to conclude that all of the sample means that you're recording at the various locations when you sample the process multiple times, or at the various timestamps when you sample the process multiple times, they will follow a normal distribution with mean mu that doesn't change, but it will have a variance which will be sigma squared over n. N being the size of the sample at each timestamp or each location, lowercase n. So this is just a central limit theorem, and there's nothing fancy about that. And you would expect that the observed sample means, what it is that you actually measure, would lie in the interval mu plus z alpha divided by 2 times sigma divided by square root of n, about 100 times 1 minus alpha % of the time for a given significance level alpha. This is exactly what the confidence interval construction tells us. Now you build what we call an upper control limit and a lower control limit. These would be the upper end of the confidence interval and the lower end of the confidence interval. And the central line is going to be mu. Notice here, none of these things depend on I. They should be the same throughout. So if you have a process, things vary over time. There's going to be some mu here, some upper limit and lower limit, and the points would fall. For the most part, we hope, within the upper limit and the lower limit, but every once in a while you might actually have observations that fall below or above. So the upper limit would be mu plus z alpha divided by 2 sigma square root of n, and the lower limit would be mu minus z alpha divided by 2 sigma divided by square root of n. Now in these charts, if you ever observe a sample mean, in a previous chart I didn't plot the sample means, I just plotted the actual observations. If you ever observe a sample mean which is above the upper control limit or below the lower control limit, then you have an indication that the process as a whole is unstable and potentially out of statistical control. Now, it's okay to have one measurement above the upper control limit or one measurement below. But if the mean is above or below, what it means is that there's a chunk of observations that are above, and that's bad. Or a chunk of observations that are below, and that's bad. The alpha is again going to be a probability of a type 1 error. What's the probability that you obtain a signal of instability, a sample mean above or below control limits, if the process was in fact stable? Now usually for statistical process monitoring, we don't use alpha 95% or 99%. We use a critical value for the standard normal distribution, which will give us that z alpha divided by 2 is 3, and the corresponding alpha for this is 99.73%. Now, if the number of time points that you're sampling or locations that you're sampling is smaller than 30, that would mean that even if you get one value outside the control limits, there's probably something off with the process, or at least we would be suspicious of the process. The reality though in practice is that mu and sigma squared are not known. You don't know what distribution these measurements come from, and so you have to provide estimates. Typically you will estimate the population mean mu with the help of the grand mean, the average of the sample means at the various time or location indices, and the radius for the control limit, 3 times sigma divided by square root of n. Well, you don't know what sigma is, but you're going to approximate it with the help of the mean of standard deviations that you've observed in your data, your S bar, and you'll actually have to modify that. So here with a factor called A3 of n, which depends on the population size. And these values have been tabulated. They show up in an actual table. Your upper control limit and your lower control limits would then be given, if you don't know the population mean and the population variance, by the grand mean of x, or x bar bar, which is something you compute from the data, plus A3n, which you can actually read from a table of control chart constants. So it would be in this column here, times the mean of the observed sample standard deviations. Lower control limit would be the grand mean minus A3n times S bar, and the center of that region, center line, would be the grand mean X bar bar. But all of these here are quantities that you compute from the data. You only need to compute 2 of them, and the coefficients that tell you how wide the control chart is going to be are given as a function of the number of samples at each sampling location or at each timestamp by reading off of a table. Now you might not have all of the exact values. Here we have for 4, 5, 6, then it jumps to 8, 10, 20. You could do some interpolation here. You're noticing that there's a pattern of decreasing values. And here you have increasing values for B3, which we'll talk about in a second. B4 is decreasing, A2 is decreasing, D3 is slowly increasing, D4 is decreasing. Whatever it is that you need these things for, consider interpolating the missing values if you don't have the right value for the n. Look at this example here. The sample mean at the 13th location, or 13th timestamp, is outside the control limits at that point. Now, that would make you suspect that the process has changed, and perhaps some investigation, some action is needed to correct the change. It certainly seems as though there's a little bit of an upward shift here. Now, it could very well turn out that, look, this is just caused by some common cause. There isn't a special cause at play. But this value here of the sample mean for all of the observations, 13th index, tells us that it's worth investigating. So what is a control chart? Well, it's going to be a succession of points that represent a sample statistic, typically the sample mean, but you can also look at other statistics that are taken from the process at different times / locations. The grand mean and the mean standard deviation, X bar and S bar for the sample statistic, are included in there, and they help you find the center line, the upper and the lower control limits, which will give you thresholds to determine if the process output is considered to be unlikely from a statistical perspective. Typically what people pick here is 3 standard deviations away from the central line. It depends on, well, what it is that you're building and what it is that you're monitoring. Sometimes you'll want 5 signals. There's optional features to these control charts. You can have upper and lower warning limits. Perhaps instead of going all the way down to 3 standard deviations away from the central line, at the 2 standard deviation distance, you'll let people know that, hey, watch out, you are going further from the central line than you might want to, and the upper and the lower control limits are not that far. You might also divide them into various zones, and you might have rules that tell you how often you are allowed to observe measurements in these zones. You could also annotate the charts for events of interest. The process quality engineers might be interested in knowing when things are different or unexpected or correspond to something that happened. Perhaps there was a visit to the factory by some governing body and you had to slow down the production lines to do a demonstration. And if there were special causes that have been and if special causes were identified, well, some description of what action was taken to remedy the situation. There's several rules that exist for flagging and detecting these process instabilities, and if you lose control over the process. What's important here is that you should clearly state and set these rules prior to the start of the statistical process monitoring. For example, you might have a rule set as follows. If a sample mean is found outside the warning limits, so between the warning limits and the upper or the lower control limit, then you flag this observation as a warning. Let your engineers know that something isn't bad yet, but it's not great. If you find a sample mean straight outside the control limits, then the process is out of control. Flag that. Stop the process. You might decide that if you have 7 successive sample means that are all above the central line or all below the central line, you say, no, that's not supposed to happen. There's supposed to be some variation above and some variation below. It would be like flipping 7 heads in a row, say, or potentially it would be more like flipping 21 heads in a row. That's not supposed to happen. Stop the production, quarantine the process, check what might be happening. Adjust the process, and then you check new samples. If everything is good, you continue the process. If not, you return to step 1. If you see a run of 7 successive sample means that are all showing improvement or all showing a decrease, well, then you might want to go back to follow these rules, 1, 2, 3. You shouldn't be seeing completely different patterns than what's been established. Now, these rules will depend on the process. It depends on the engineers that are running the processes. It'll depend on the stakeholders. It'll depend on a number of things. If you're running statistical process monitoring for vaccination production, you might have more stringent rules than if you're running statistical process monitoring for these fidget spinners that used to be so popular a few years ago, right? Because if it turns out that you're sending out fidget spinners to market and 1 out of every 50 of them is defective, not that big of a deal. But if you're sending out vaccine batches and 1 out of every 50 of them is defective, that's actually a pretty big deal. You can produce charts for the sample mean using other measures of the spread in your distribution. We've talked about how you may approximate the standard deviation by the range, or at the very least how the range can provide you with some measure of the spread. So here, for every timestamp or for every location of interest, rather than computing the sample standard deviation, you might compute the range, which is to say you will find the maximum value of all the sampled observations, and you'll subtract from that the minimum value of all the observations. That gives you an idea of the spread in the distribution. The mean of the ranges is R bar, as you would expect. So when you go through the process, you sample from each timestamp, from each location, n observations, you will get capital N ranges. This is the number of timestamps you have. And R bar is going to be the observed value of the mean of the ranges. Then you would get different upper control limits, lower control limits. Instead of getting an upper control limit as X bar plus A3N times S bar, you're going to use the range here. You just need to use a different type of coefficient. It's the A2N coefficient. The lower control limit is given by X bar minus A2N times R bar, and the central line is X bar. So this isn't going to give you the same control chart. It just gives you a different way to monitor the sample mean, using the range of the values instead of using the standard deviation or the sample standard deviation. When would you use this instead of the sample variance? Well, you'd use this when you have a very small number of points that are being audited at each timestamp or at each location, where you don't know that you can trust the estimate for the sample standard deviation if you have fewer than 10 points in your sample. It's just not big enough of a sample. Again, these A2N coefficients are given in tables of coefficients. Now be careful, different books define these things differently. So be sure that whatever table it is that you're using is coherent with how you're defining your control charts. There's other charts that you can build. Instead of monitoring the sample mean, you might be interested in monitoring the standard deviation, in which case you would use different control chart. The center line here would be the mean standard deviation, S bar, which you compute from the data, and the upper control limit and lower control limit would be given by B4N times S bar and B3N times S bar. And here, perhaps it's not clear from my drawing, these do not have to be the same length. So when you build a sample mean chart, an X bar chart, either from the sample standard deviation or from the range, you have to have a symmetrical upper control limit and lower control limit. This is not the case for the S chart. If you're monitoring the sample standard deviation, it's conceivable that you will not get a symmetrical chart. If instead you're monitoring the range of the observations, you also get potentially a non-symmetrical chart. You can actually monitor the observations themselves rather than monitoring the actual sample mean or the sample standard deviation. And here you'd be plotting all of the observations, and if any of the measurements fall above or below, you'd be flagging it as being out of control. Because the sample mean has a tighter standard deviation than the observations themselves do, thanks to the central limit theorem, you would expect here that for an observation chart rather than a sample mean chart, the upper control limit and lower control limits would actually be wider. This is given here by the fact that you are going to be multiplying these things by the square root of n here. So typically speaking, the radius, if you want, of the charts when you're looking at the observations themselves rather than trying to monitor the sample, you have more margin for every once in a while getting a crazy measurement. So you can either measure those from the range or from the sample standard deviation. As before, if n is smaller than 10, you should probably chart it using the range, the observed range, and if it's greater than 10, the number of audits at every timestamp, every location, then you would build your chart using this formulation here. You will not be getting the same chart, and these are different charts. The chart from R and the chart from S, just a different way to approach the problem. Here's a few examples to make this clear. Imagine that a company produces a storage console. Twice a day, you test 9 critical characteristics on 5 consoles that you select randomly from the production line. One of the characteristics that you measure is the time it takes the lower storage component door to open completely. And it should be within some sort of preset requirement. On the next slide, we'll see a table that lists the opening times in seconds for the consoles that were tested for 1 week. So n equals 10, so we'll look at 10 different locations from which to sample the production line, and then we'll sample 5 consoles at each of these locations. So in the table we also show the computed sample mean, sample standard deviations, and the sample range. I've extracted here the control chart coefficients that you might be interested in using. So because we sample 5 observations from each group, from each location, from each timestamp, we have coefficients A25, A35, B35, D35, B45, and D45. So these are all values that you can extract from a given table. We're going to build the control chart for the sample mean from the sample standard deviation. We'll also build an S chart, a chart for the sample standard deviation, and we'll build an observation chart for the sample mean from the range, as well as building a range chart. So there's 4 types of observations that we will monitor, hoping that we can identify when any one of these things is off kilter. And the conclusion we'll get is that the 5th group, so the samples from the 5th location, should be investigated further. Let's take a look at this. So here is the data. As you can see here, I have my uppercase N groups and locations. For each of them, I've taken 5 consoles randomly, and I've measured the time to complete opening. I then have the average for the 5 consoles, the sample standard deviation, and the range of times. And because I will need them, I compute the grand mean, the mean of the sample standard deviations, and the mean of the ranges. These are all the quantities that I need in order to be able to build my control charts. What we see here is that the sample means are, for the most part, within the upper control limit and the lower control limit. Right? This is meant to be, roughly speaking, 3 times sigma divided by square root of n, except we don't know the true sigma, so this is approximated with the help of the other coefficients. There's a few instances. I mean, look at this one here. It's close to the upper control limit. It's right on it. And this one is just a little bit above. Technically, we should be flagging this. This one here is well below the lower control limit. So if we just follow the sample means, there's definitely one that should be looked at, and there's 2 other ones here that we think are problematic. Now, let's see if we recover the same type of situation, or the same type of flags in the other charts. Here I am charting the sample standard deviation for my observations, and everything seems to be falling well within the bounds that I would expect to see. So this one seems to say there's nothing to flag here. And this one, I'm charting the range of my measurements, and again, well within what I would expect for the control chart. So everything seems to be fine for this one as well. If I look at the actual observations, at each of the groups, well, this is my 1 bit here. You'll notice the central line is the grand mean in both instances. That doesn't change, but now I'm allowed to have actual observations going way above the value of about 1.44, which was the upper control limit for the sample mean. It's not the upper control limit for the observations. The observations are allowed to range beyond that upper limit for the sample mean. It can go to about 1.81, and it seems here that all of the observations are within, so that's acceptable. I mean, we are seeing that for group 1 here and this group here, the observations are all above the grand mean, but that's not completely unacceptable. You at least have some observations close to the grand mean. This one here, though, it is within the allowed range, but there's no observation very close to the grand mean. Coupled with the fact that the sample mean is well outside of the control chart for the sample mean at that specific location for group 5, we should probably look at group 5 further. And group 1 we might want to look at as well, but look, there's a fair number of points that are well within the range of observation. It doesn't seem as pressing a problem. And I do want to highlight that the control charts for the standard deviation and the control chart for the range, they are not symmetrical. This distance here is a little bit below 0.5. This distance here is actually a little bit above 0.5. Similarly here, this is 0.2, close to 0.2. Here, this is a little bit more than 0.2. It's important to remember how to compute these control limits. Well, depending on the type of chart, and depending on the value of the grand mean, and the mean of the sample standard deviations, and the mean of the sample ranges, which are obtained here, and depending on the number of observations you are sampling everywhere, you'll get different coefficients, and then you compute the control limits with the help of either these expressions here, or potentially this one, or potentially this one here. Okay? Here's another example. Let's say that there's n timestamps, or n locations, n equals 5, and you will sample 4 products from each of the locations, from each of the timestamps. You make your measurements. What would you say about the measurements that you're seeing here? Well, we can compute definitely the sample mean for each of the location timestamps, the range, the standard deviation. We compute the grand mean, the mean range, and the mean standard deviation. And because we have 4 samples at each location / timestamp, we will need to have the values of coefficients when little n is equal to 4. These are the values that you would read from the table. Well, what can we say about this process? You can actually do this in R as well. I mean, you can build these things by hand. It's doable, but it's a little bit time consuming for no good reason. There's a package called QCC and R that would allow you to do that. So I've created a data frame here with these measures. For the sample columns, you can run the code that I've provided you in these slides. I will not explain it, but I think it'd be worth your while to try it. The only thing I'll tell you is that we set 2 different types of warning limits at 1 sigma and at 2 sigmas. And we'll build a number of charts. I'll show them in the following slides together with the summaries. So this is a chart for the sample mean. What we're seeing here, number of groups is 5, that's capital N. We have the center line, the grand mean at 28.21. We get a lower control limit at 22.03224 and upper control limit at 34.38776. There are a number of default rules in there, but what we're seeing is that no sample means are outside of the limits, and there's no violating runs. Presumably, if you had too many increasing values, or too many values above the grand mean, the center line, this would be flagged by the routine in R. So if you just look at the sample means here, nothing seems out of the ordinary. Although, to be fair, that last observation has crossed the second warning line. You can build a chart for the sample standard deviation. These 4 measurements. Again, you get all of the information you might want from here. The center line is there. We get a lower control limit at 0, an upper control limit at 8.50. We can clearly see here that this region is larger than this region. That's acceptable. Nothing goes beyond the limits. There's no violating run. Again, we don't think there's anything wrong with the standard deviations amongst our groups. If you look at the chart for the ranges, and now we're starting to get close to the upper control limit. Look back here for a second. Something was, close to the upper control limit for the standard deviation as well, and well, it was a bit of a warning here for the sample mean. It certainly seems as though something is happening with group 5, which is not like the other ones. You can sort of see what the culprit observation would be. This observation here is actually smaller than you might expect. Still not small enough to really flag the process as being out of control, but we have some indications here, some warnings that things aren't as great as they could be. In fact, if you were to change one of the entries in the table, the entry in the 4th column of the 5th row, so this one here, instead of 22.0, perhaps you mistakenly entered it as 2.0. You would actually get flagged as having a sample mean that is beyond the limits. I will finish this by warning you that there are a number of people who doubt the validity of statistical process monitoring, especially if it is followed blindingly. All you're really trying to do is to find out if there are any of your values that are unusual enough for you to look into what's happening. But how these quantities here are computed, the A2, A3, B3, D3, B4, D4, coefficients for various values of n, we make a lot of assumptions to get coefficient values here. This is not a completely controversy-free approach or application of statistical analysis.